Section 300.50 of the National Electrical Code, or NEC, addresses underground raceways, which would cover the installation of a concrete trench and lid, sometimes referred to as trencher, used for housing high-current cables. This specific scenario involves 735.2 kcm locomotive type cables, each rated at 732 amps, running from a 480-volt 2285 kVA generator to a 2500 kVA transformer over a distance of approximately 30 feet. The NEC provides guidelines to ensure the safe and efficient operation of such installations. When installing single conductor cables, grouping them by phase and maintaining proper spacing is crucial. Specifically, the question references spacing the cables at 2.15-inch intervals, as outlined in cable tray specifications, adhering to Articles 392.80 and 392.1b4. Grouping conductors by phase helps to balance the magnetic fields and minimize inductive reactance, which in turn reduces voltage drop and improves overall system performance. Maintaining the specified spacing is also important for heat dissipation. When conductors are bundled too closely together, they can overheat, leading to insulation degradation and potential failure. The NEC provides tables and guidelines for determining the appropriate ampacity of conductors based on their size, insulation type, and operating environment. If the cables are not grouped by phase and spaced according to the specifications, Article 310.15b2 requires that the ampacity of the conductors be derated. In the described scenario, the cable should be derated to 50% of their normal ampacity rating. This derating is necessary to account for the increased heating that occurs when conductors are not properly spaced and grouped. Without adequate ventilation and heat dissipation, the conductors can overheat, leading to premature failure and potentially creating a fire hazard. Therefore, adhering to the NEC guidelines for conductor grouping, spacing, and ampacity derating is essential for ensuring the safe and reliable operation of electrical systems. The installation of electrical cables in underground raceways, such as concrete trenches, presents unique challenges that must be addressed to ensure safety and reliability. Firstly, the underground environment can be harsh, with exposure to moisture, temperature variations, and physical stress. These factors can accelerate the degradation of cable insulation and increase the risk of electrical faults. Secondly, the close proximity of multiple cables in a trench can lead to increased heat buildup, which can further exacerbate the degradation process. Thirdly, the potential for ground faults and other electrical hazards is higher in underground installations due to the presence of moisture and other conductive materials. To mitigate these risks, the NEC provides specific requirements for the installation of underground raceways and cables. These requirements cover a wide range of topics, including the type of raceway material, the depth of burial, the spacing between cables, and the ampacity of conductors. One of the key considerations in underground cable installations is the type of raceway material. Concrete trenches are a common choice for high current applications due to their strength, durability, and fire resistance. However, it is important to ensure that the concrete is properly cured and sealed to prevent moisture from entering the trench. Moisture can damage cable insulation and create a path for ground faults. Another important consideration is the depth of burial. The NEC specifies minimum burial depths for different types of raceways and cables to protect them from physical damage. For example, direct buried cables typically require a deeper burial depth than cables installed in rigid metal conduit. The spacing between cables in a trench is also critical for heat dissipation. As mentioned earlier, closely spaced cables can overheat, leading to insulation degradation and potential failure. The NEC provides guidelines for determining the appropriate spacing between cables based on their size, insulation type, and operating environment. In addition to these physical considerations, the NEC also addresses the electrical aspects of underground cable installations. This includes requirements for grounding, bonding, and overcurrent protection. Grounding and bonding are essential for preventing electric shock hazards and ensuring that fault currents can safely flow back to the source. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect cables from damage due to overloads and short circuits. Proper installation of high amperage cables in a concrete trench requires careful attention to detail and a thorough understanding of the NEC requirements. By following these guidelines, it is possible to ensure the safe and reliable operation of electrical systems in underground environments. To delve deeper into the technical aspects, let's consider the specific NEC articles mentioned. Article 300.50 focuses on underground installations. It mandates that underground circuits be protected from damage. The trench itself needs to be structurally sound and capable of withstanding the weight of the cables and any potential traffic above it. The covers must be securely fastened to prevent accidental removal and unauthorized access. Furthermore, the trench should be designed to prevent water accumulation, which can compromise the insulation of the cables and create a hazardous environment. Proper drainage is essential. Articles 392.80 and 392.1b4 pertain to cable trays. Even though the cables are in a trench and not a traditional cable tray, the principles of cable management and spacing still apply. Article 392.80 addresses the ampacity of cables in cable trays. It emphasizes the importance of maintaining adequate spacing between cables to allow for heat dissipation. When cables are bundled together or placed too close to each other, the heat generated by the current flow can build up, reducing the ampacity of the cables and potentially causing them to overheat. Article 392.1b4 provides specific guidelines for spacing single conductor cables in cable trays. It recommends spacing the cables at least 1 cable diameter apart to allow for adequate ventilation. In the scenario provided, the cables are to be spaced at 2.15-inch intervals, which should comply with this requirement, assuming the cable diameter is less than or equal to 2.15 inches. Article 310.15b2 deals with ampacity adjustment factors for ambient temperature and the number of current carrying conductors. When multiple conductors are installed in close proximity, the heat generated by each conductor can raise the ambient temperature, reducing the ampacity of the cables. Article 310.15b2 provides tables and formulas for calculating the ampacity adjustment factors based on the number of current carrying conductors and the ambient temperature. In the scenario provided, if the cables are not grouped and spaced properly, the NEC requires that the ampacity of the conductors be derated to 50% of their normal ampacity rating. This is a significant derating factor, and it highlights the importance of adhering to the NEC guidelines for cable spacing and grouping. The purpose of derating is to ensure that the cables do not overheat and fail, even under worst-case conditions. The NEC specifies ampacity derating for several reasons. Firstly, heat generated by electrical current flowing through conductors raises the conductor temperature. Secondly, excessive heat degrades the insulation and reduces the lifespan of the cable. Thirdly, overloading conductors can create a fire hazard. Fourthly, derating ensures conductors operate within safe temperature limits. Fifthly, it accounts for ambient temperature and conductor proximity. Sixthly, derating factors are found in NEC tables like 310.15 bone and 310.15b2. Seventhly, ambient temperature correction factors adjust ampacity for temperatures above 30 degrees Celsius. Eighthly, the number of conductors adjustment factors reduce ampacity when multiple current carrying conductors are bundled together. Ninthly, derating prevents thermal runaway, where increased temperature leads to increased resistance and further heat generation. Tenthly, the NEC provides guidelines for specific conditions such as conduit fill and direct burial. The application of these NEC guidelines requires a thorough understanding of electrical principles and a careful assessment of the specific installation conditions. It is essential to consult with qualified electrical engineers and contractors to ensure that all aspects of the installation are in compliance with the NEC and other applicable codes and standards. In summary, the NEC provides comprehensive guidance for the installation of high amperage cables in concrete trenches. By adhering to these guidelines, it is possible to ensure the safe, reliable, and efficient operation of electrical systems. The NEC guidelines cover various aspects of the installation, including raceway selection, cable spacing, ampacity derating, grounding, bonding, and overcurrent protection. Proper planning, design and installation are essential for minimizing the risks associated with high current electrical systems. The specific articles mentioned provide detailed requirements for cable trays, underground installations, and ampacity adjustments. It is important to consult these articles and other relevant sections of the NEC to ensure compliance with all applicable codes and standards. Additionally, it is recommended to seek the advice of qualified electrical professionals to ensure that the installation is properly designed and executed. This includes proper selection of cable sizes, insulation types, and termination methods. It also includes ensuring that the grounding and bonding systems are properly installed and tested. Furthermore, it is important to conduct regular inspections and maintenance to identify and address any potential problems before they can lead to equipment failure or safety hazards. The NEC also emphasizes the importance of proper documentation. All aspects of the electrical installation should be thoroughly documented, including the size and type of cables, the routing of the cables, the location of all equipment, and the results of all testing. This documentation can be invaluable for troubleshooting problems and making future modifications to the system. In addition to the NEC, there may be other applicable codes and standards that must be followed. These may include local building codes, fire codes, and environmental regulations. It is important to be aware of all applicable requirements and to ensure that the installation is in compliance with all of them. The ultimate goal is to create a safe and reliable electrical system that meets the needs of the facility and protects people and property from harm.